Alright, in this video we're going to talk about graphing rational functions, and I have another video that I did before this that talks about in a little bit more detail how to find each of the things that we're going to start off finding. And so if all of that is going over your head, you should try to look for that video that's called Rational Functions and Asymptotes, or try to Google it and find some other video, because this is something that you kind of have to already have those skills, or it's nice to have those skills already before you start trying to just jump in right here. Because what we want to do each time that we start one of these problems is we want to be able to find some things, and the things we want to be able to find are our horizontal asymptote, or HA as an abbreviation. We want to know if there's any holes in our graph. We want to know if there's a vertical asymptote or multiple vertical asymptotes. And then it's also nice to know about any x-intercepts. And then on top of that, we are probably going to have a table of values that we want to use to help us plot some points. So all of that together, like all of that except the table of values, is what I talked about in the other video. And so now we're going to find those things, but then put them onto a graph to see how that works. So our horizontal asymptote has to do with whether there's more x's on top or on bottom. And so there's not an x on top of this at all. There is an x on bottom. If there's more x's on bottom, that makes this be y equals 0 for our horizontal asymptote. Horizontal means that we have a horizontal line at y equals 0. So that's going to be this line that's basically on top of the x-axis. And so what that's doing is that's going to keep our graph from crossing the line y equals 0. The next thing we do is we try to factor the top and the bottom. This doesn't factor. If it doesn't factor, that means nothing will cancel, so this doesn't have any holes. And these first ones we do, a lot of them aren't going to have holes because it kind of is a step up in complications or whatever for this. So the vertical asymptotes we get by setting the bottom equal to 0. And so the bottom, if I set it equal to 0 and solve, I subtract 3 from each side and get x equals -3. So there is a vertical asymptote at -3, which means I can draw a vertical line at -3. Then my x-intercepts happen where the top equals 0. Since 1 can't equal 0 and there's not an x to solve for or anything like that, that means that there's not an x-intercept. And so what happens is these graphs all look really similar to each other. So once you've seen 2 or 3 of them, all the rest of them look the same basically. So either our graph is going to be in the top right and bottom left in these two spaces that are diagonal from each other, or it could be in the top left and the bottom right. And so us making a table of values is how we figure out which of those things is happening. And so we can either pick points ourselves, like we can pick 0 and think about what happens when I plug in 0 here. I'd get 1/3. And I can do that for some points and just try to think about it. Like -1, if I plug it in, gives me 2 on bottom, so that's 1/2. And then -2, I get a 1 on bottom, so that gives me 1. And that helps me figure out some points that I can plot. Because as I get to the right here, I should be getting closer and closer basically to the asymptote that's happening. Like if I plugged in 1, it should be an even smaller fraction, and so on. So if I plugged in -2.5, I should end up being up here somewhere maybe. And so as I go up, it's like this is a wall that I'm getting closer and closer to. And like this is like the floor that I'm getting closer and closer to. If I want to know what's happening on the other side of this asymptote, I could plug in like -4. And if I plug in -4, I get -1 on bottom, so that gives me -1. And so the same kind of thing is going to happen down here, that I'm going to get closer and closer to this asymptote and closer to this asymptote. Now what we can do basically at any point along the way here, unless your teacher doesn't want you to use a calculator at all, is you can put this in the calculator into y equals as 1 divided by x plus 3. If you're calculator doesn't do fractions, make sure that you put the bottom in parentheses, or even putting both the top and the bottom in parentheses would be fine. If I graph this on my calculator, this won't be exactly what your TI shows you, but this is a website called Desmos that does a pretty good job of graphing. Actually, it does a really good job of showing you what graphs look like. So you can see like that we have a vertical line at -3, an imaginary vertical line at -3 that our graph is getting closer and closer to, an imaginary line at y=0, and then our graph is in the same places as what we said it should be. And so if we hadn't already graphed it, this would help us know where to draw our graph just by looking at this. So a lot of graphs are going to look really similar to this, including the next one, like 2x minus 1 over x. Like, in some ways that's super different than what we just had. Like, there's x's in different spots and numbers in different spots, but once it comes down to it, we're going to find a lot of similarities. So I want to do all of these things. My horizontal asymptote, I look at the biggest x on top, meaning the x with the biggest exponent, the x with the biggest exponent on bottom, and I compare them. Since they're both x's, it's kind of like you can think of it like this. This is what's going to tell us our horizontal asymptote. If I have 2x over x, my x's would cancel, and that would leave me with just 2, because this is like 2 over 1. That's what my horizontal asymptote is going to be, is just 2. Now the -1 that's on top doesn't really go away like forever. Just as far as our horizontal asymptote goes, we only care about the two biggest x's, like the x's with the biggest exponents. So I can draw a horizontal asymptote at 2 over here, just to start. So it's kind of like the last one, except for it's been moved up 2 spaces. I can't factor the top or the bottom of this, which means nothing is going to cancel, so there's not going to be any holes. When I set the bottom of this equal to 0, I get my vertical asymptotes, and so there's just a vertical asymptote at x equals 0. So that's a vertical line now that's on the y-axis. My x-intercept is where the top equals 0. So if I solve 2x minus 1 equals 0, I would add 1 and then divide by 2, which gives me x equals 1/2. What that means is if I make a table of values, I know that at 1/2 for x, my y value should be 0. And so if we didn't do that, we probably wouldn't know that. Like if I look at on my calculator at a table of values, 1/2 is probably not going to be on there. So that's just an extra point that is actually helpful for us to be able to draw. If I think about plugging in 1, I get 2 minus 1 on top, which is 1, over 1 on bottom, which is 1. So I can plot 1, 1. And then I can say, okay, well, from the last one, or from plugging this into my calculator, I know that it's supposed to go up towards this asymptote and down towards this asymptote. It gets closer and closer and closer, but it never actually is supposed to touch. It gets super, super close, but not ever there. Like when you used to play the game with your siblings or friends where you're like, I'm not touching you, and you like put your finger like really close to their face, as close as you possibly can without actually touching them, and it makes them mad. And yeah, so if I plug in like -1 up here, I'd get -2 minus 1, which is -3 over -1, so that gives me +3. Now, I'm pretty good at like mental math and stuff, so to me, that whole process isn't very hard. So if you're not so good at mental math, what you would want to do is type this into y equals on your calculator and then press second graph and look at the table of values. And on that table of values, it'll have these points. In between there, it'll say 0 and it'll say error, because that's where this asymptote is. And you'll also, if you plug it into your calculator and press a graph, you'll be able to see what the graph actually looks like. And so you'll see how it compares to what we have right here. I graphed it over on that website already. And so this is what it looks like. See, we have a horizontal asymptote at 2 right here. We have a vertical asymptote up here at 0. And like it has the point like right here, 1, 1. I apparently don't know what I'm doing here. If I click 1, 1 is a point that we found. We knew it was 1/2, 0. So all of those things we found really are what this graph looks like, which is pretty neat. Let's make things a little more complicated. So the two that we've already had are kind of the graphs that you get whenever you have one vertical asymptote, but sometimes there's more than one. You'll only ever have one horizontal asymptote. You don't ever end up with more than one of those, but vertical asymptotes we can end up with more than one. So if I go through my list of things here and write them down before I start. All right, what we want to do is find the horizontal asymptote. So this x to the first on top and this x squared on bottom is what I care about. And I'm going to say, all right, there are more x's on the bottom because an x squared just matters more for a horizontal asymptote than an x to the first. And because of that, the bottom of this outweighing the top is going to make our horizontal asymptote be y = 0. This has to do with the fact that, like, we're talking about plugging in numbers for x, and so if I plug in a really big number for x squared, like infinity, but on top I have infinity to the first power, which of those is actually going to win out? It's going to be the infinity that's on the bottom. And 1 over a really, really, really big number is going to get closer and closer and closer to 0. So like if you did 1 over 1,000, that gives you 0.001. But if you keep adding zeros to the bottom of that, you get closer and closer to 0. If you're doing it on your calculator eventually might round to 0 even. But that's what's happening there, is that if I have more x's, if a bigger exponent on bottom, it's going to get closer and closer to y = 0. So here's our horizontal asymptote. To find the rest of these, we need to start off by factoring. 3x does not factor into anything. It just stays 3x. But on the bottom, we can say what multiplies to get -2 that adds to get +1, which will be a +2 and a -1. And what we can do is say, well, since nothing cancels, because I don't have just an x on bottom and I don't have an x + 2 or an x - 1 on top, nothing cancels, so there's no holes, which means both of these things on the bottom are going to be vertical asymptotes. So we'll have a vertical asymptote at -2 and at +1. Our x-intercepts come from the top of this, where we set it equal to 0. If I do 3x = 0 and divide both sides by 3, I get x = 0. So my vertical asymptote at -2 and +1. And then my x-intercept is at x = 0. And as soon as you try to put this dot on 0, you might be like, well, hang on a second. How do I have an x-intercept at 0 whenever I have a horizontal asymptote at 0? And so this is one of those things where horizontal asymptotes, to be perfectly honest, are not always very good at doing their job. Just like if you've ever had a job yourself, you know that some employees are better at their job than others. And so this is a weird thing to talk about in mathematics, because we're used to mathematics like being pretty sure of themselves most of the time, concept-wise, like they always work, right? Well, horizontal asymptotes in the middle just aren't very good sometimes, and it's on the outsides that you can rely on them to actually be good at keeping your graph from crossing. So from here, we would either have to plot points ourselves or plug it into our calculator and look at a table of values. I'm going to pull up my graph and show you what this should look like. And it looks both similar and different from what we have just graphed before this, because this part on the left and the part on the right, that should look really similar to what we've been doing. But the part in the middle, this looks kind of like almost like a cubic function in between the two vertical asymptotes we have, and it's going through 0. So to the best of our abilities, we're going to try to make this picture appear on our paper now. And so it doesn't, in my opinion at least, if you have a different teacher, they might be more picky, but it doesn't have to be like a super intense drawing. It just has to get the point across. So we've got this squiggle thing in the middle, and then it was up here, headed to both asymptotes, and then down here, headed to both asymptotes. And I have a habit of accidentally like making the line go back away from the asymptote, and like that's not right. It's just supposed to get closer and closer without touching. So that's, I mean, I don't think that drawing looks super good, but it gets the point across. A lot of times with teachers, it's more important that you've shown that this stuff is true and that you've made it look like those asymptotes really are on your graph and things like that, more so than like having every single point plotted perfectly, which is really alliterative, by the way. Let's try another one. And this is going to look, again, similar but different. And after this one, we'll have pretty much seen, as long as we have a horizontal asymptote, kind of the three types of graphs we're probably going to see. So let's go down our list. Okay, so our horizontal asymptote, we have x squared on top and x squared on bottom. So we're basically saying negative 2x squared over x squared. What does that give me? It gives me a negative 2 over 1. So my horizontal asymptote is negative 2. It's only when we look for our horizontal asymptote that we're allowed to just ignore the negative 9. We're not saying that those things really do cancel out, because they can't because of the negative 9 on bottom. We're just saying if that negative 9 wasn't there, because it doesn't have an x, so in the broad scheme of things, it's really not going to make a difference for our horizontal asymptote, then what would it be if we canceled these out? Let's factor the bottom of this. So x squared minus 9 splits up into x plus 3 and x minus 3. And nothing cancels here because there's not an x plus 3 or an x minus 3 on top. There's not an x or an x squared on bottom. So again, we have no holes. I think we'll have holes on the next one. So if you've been worried about there not being any holes, don't worry. It'll happen soon. We set the bottom equal to 0 to get our vertical asymptote. So there's one at positive 3 and one at negative 3. We set the top equal to 0 to get x-intercepts. And so if I set this equal to 0, I divide by negative 2 and get x squared equals 0 divided by negative 2, which is still 0, and then I square root, and it's still 0. So if you realized it was 0 without doing all that work, that's great, but if you have to actually sit there and solve it just to make sure, that's fine too. That's the process we would go through, and we'd still end up with 0 there. So now we just need to go ahead and draw what we know. So negative 2 is our horizontal asymptote. Negative 3 and positive 3. This is going to end up being symmetric, which I personally am a big fan of symmetry. Our x-intercept is at x equals 0, and so this is going to, again, be similar to what we've done before, but also different. If I pull up what this graph looks like, and in my opinion, it's not that big a deal if you have to look at your graphing calculator. Like, I have to check my graphing calculator or plug in points to make sure I really know what I'm looking for, and I know that not everybody's good at plugging in points themselves. So this is different than what we had before, because in the middle, in between our asymptotes, we have what kind of looks like a parabola, and then our graph is down here at the bottom left and the bottom right. So if I try to put that on my graph, I'm going to draw up towards my vertical asymptotes on either side in the middle. And then down here, I draw towards my asymptotes. And so when you're doing this, like the first two examples I did, my asymptotes, there was one of each, and so they formed a T. And so either I was going to have a graph up here and down here. That was one option, or I could, given a negative or something, I could end up with it here and here. So the other kind of graph we see is if I still have one horizontal asymptote, but I also have 2. So it almost makes a tic-tac-toe board. And so we saw in the third one I did that you can have like a squiggle in the middle and then have graphs over here and over here. But then the other case, which is this one right here, I wonder if this color shows up. Probably not very well. We have a parabola and then we have them down here on this side. And we could have flipped of both of those options as well, like if it was flipped over the x-axis. And aside from what I've just drawn, like there's not really many other options unless we don't have a horizontal asymptote. If we don't have a horizontal asymptote, our graphs can start looking pretty crazy. And we'll see that in a second because I'm going to do, I believe, 2 more examples. One has a hole, one has a slant asymptote, so we'll see what else can change on our graphs based on that. JK, there's 3 more examples, and this one, no, I'm wrong, there's 2, because this has a hole. Okay, here we go. Horizontal, holes, vertical asymptote, and x-intercept. Again, if you don't really know how I'm finding these things, either Google rational functions and asymptotes, or look on my YouTube channel for the video that was uploaded right before this one. What we want to do is for our horizontal asymptote, we just want to look at these x squareds and say, if I have x squared over x squared, what does that cancel and give me? Since there's ones, these are 1 x squared and 1 x squared, it gives me 1. So my horizontal asymptote is at y equals 1. Then I factor to find everything else. So the top factors into x plus 3 and x minus 3. The bottom factors into what multiplies to get -3 and adds to get -2, which is -3 and +1. Okay, so this is what we haven't had happen before in this video. The x minus 3 on top and bottom is something that we can cancel because they're the same. And so we have a hole where x minus 3 equals 0. And so it's not going to be at -3, our hole is at +3 because we have to solve that. When we're graphing, that's the very last thing we're going to do is put the hole at x equals 3. Everything else is going to work the same way as what we've been doing. Our vertical asymptotes is where the bottom equals 0. So the x equals 3 from the hole, it only goes in this whole spot. So my vertical asymptote, I only have 1 at the part that didn't cancel. So I have a vertical asymptote at x equals -1. The top equal to 0 is my x-intercepts, and so I only have 1 x-intercept at x equals -3. So I am going to graph this. So at y equals 1, there's a horizontal asymptote. And then at x equals -1, and then I can draw my x-intercept at -3, like this graph goes through the x-axis at -3. And so if this is the shape of my horizontal and vertical asymptote as like a kind of like a T or a cross, and because it goes through at -3, I can be reasonably sure that it's going to go up this way and down this way, and then it should be over here in this diagonal as well. One thing I can do pretty easily is if you plug in zeros where all your x's are, you can find your y-intercept and get 3. So I can know, hey, it goes through right there, and I can draw. And so if I do that, I've done everything except for the hole. So here's how holes work, is that you graph it as though there isn't a hole, but then you look back and say, okay, at 3, there's a hole. So erase what you drew, and you're going to put an open circle on your graph at that spot. So at 3, which is right here, there's a hole. So I erased my graph and I put a hole there. The problem that we find is that if you just graph this on your calculator, it's not very good at telling you about that hole at 3. It doesn't show up in your graph. Even if I put this on this website and I pull up what it looks like, it does not actually show me the hole that's right here at 3 because it's more concerned about other things whenever it's graphing than showing us that there's a hole there. Now, if I go to my table of values on my TI calculator, or on this one, if I come over here and try to figure out what's happening at 3, if I can land on it, because that's tricky apparently, you can see it flat there. 3 is undefined. There's a hole at 3 because nothing is happening there because it makes the bottom of my fraction equal 0. If you go to on your calculator to your table of values, it should tell you there's an error at 3. But as far as the picture on your graph, it doesn't show you. So you have to know to put that open circle there to show that there's a hole there. And that's the only thing that's really different than what we did before, is just figuring out where the hole should be and making sure to put it on your graph. The only other thing I'm going to do now is talk about slant asymptotes. And so the third case for a horizontal asymptote is that there's not one. And this happens if the degree of the numerator is greater than the degree of the denominator. If the degree is the exponent. So here x squared is bigger than x, so there's not a horizontal asymptote. There's a slant asymptote, and we can find it using long, or we're probably going to use synthetic division unless we just can't use synthetic division. So with synthetic division, because we're going to find the slant asymptote of this real quick. Synthetic division is where what you're dividing by, if it's a factor like this, you first have to say, well, what is that set equal to 0? Which in this case is -1. And then you write down what's in front of these, which is 1 and -1. And then we would need to think about this like there's also a +0 at the end. And we do synthetic division, which if you don't know what that is, go and Google it and you can find a video of that as well. So what it does is it tells us our slant asymptote. It tells us about a diagonal line at y equals, this will be 1x minus 2, and we just ignore the remainder and pretend like it's not there. It's the only time it's okay to ignore the remainder when you divide is when you're finding slant asymptotes. What this means is if I graph this and I graph the line that starts at -2 and then goes up 1 and over 1, that this is the asymptote that I have for this graph. It has a vertical asymptote at -1. And so what happens is that my graph, instead of being almost like an L and the opposite of an L, is going to be kind of off kilter, because either my graph is going to be here and here in these skinny spaces, or it could be on the other side here and here. And what it does is it follows along the asymptotes either way, depending on which one of those two cases it is. And without plotting points, I don't know which of those two cases it is. So let's look at a problem that we're actually going to do all the way through. X squared minus x minus 2 over x minus 1. We're going to graph this, and so we're going to find the horizontal asymptotes, the holes, the vertical asymptotes, and the x-intercepts. And you can actually find these in any order you want. I like to do it in a certain way because I think it's easiest. Like my horizontal asymptote, I want to look at before I actually factor. And so I say, well, there's more x's on top than bottom. So there isn't a horizontal asymptote, but there will be a slant asymptote that we find by dividing. If we want to go and do that, then what happens is you set the bottom equal to 0 and get 1. You put the numbers from the top, and we do synthetic division. I drop the first number, and then I multiply, add, multiply, add. And all I care about is the first two numbers. This is my x, and this is my number. So my line is y equals x plus 0. You don't have to write the plus 0 there, but we might find it helpful in a second when we decide to graph this. I'm going to factor on top and bottom. And I say what multiplies to get -2, that adds to get -1, which is -2 and +1. Nothing cancels, so there's not a hole. But I set the bottom equal to 0 and get x equals 1 as a vertical asymptote. I set the top equal to 0, and I get 2 and -1. So if I start to put this on my graph, to draw this horizontal, well, this slant asymptote, y equals x plus 0, you start at the number on the y-axis, so this axis. You start at that number and then you use your slope, which is 1 over 1. If you're not good at graphing, you can type in y equals x as one of your things in your calculator to help you and get some points that way. But this is our slanted line that we need for our slant asymptote. Our vertical asymptote is at 1. And then we have an x-intercept at 2 and an x-intercept at -1. Well, because of where my x-intercepts are, I can tell personally what that means my graph is going to look like, but these graphs look kind of weird, so I'm going to show you what this graph looks like on, something that's better at drawing it than I am. So the asymptote is at y equals x, and so you can see, like, if this red line is y equals x, look, my graph is getting closer and closer to it. If I zoom out, it almost looks like it gets on top of it, but it's just getting so close and my lines are so thick that it makes it look like they're basically ending up as the same line. So when I draw that, what I care about is that it's the bigger kind of graph, the one that's wider or whatever. But since I know where my x-intercepts were, that also would help me know where to graph this. So it should look like this. So there you have it, graphing rational functions.